Dr. Nagala Prabhakar Rao Garu, the Department of Mathematics is organizing a one-week international faculty development program on innovative applications of mathematics in association with the Institution's Innovation Council, ICC BEC. In fact, today is their birthday. Now I will present our department profile. The department was established in the year 1981, in which the college was started. The department, which was originally intended to cater the needs of engineering, offered MSc Mathematics course with an intake of 40 students in the year 1989. The department was recognized as a research center by Acharya Nagarjuna University from the academic year 2003-2004. The department got name and fame under the leadership of former head of the department, Dr. Nagala Prabhakar Rao Garu. So far, the department produced 3 PhDs and 13 MPhils. The department was recognized as one of the potential departments in 2002 by National Board of Higher Mathematics. And as a part of it, the department has been receiving quality books in mathematics, which are very useful for students and staff for their higher learning and in their research. The department is now enriched with 5 PhD faculty members from different universities. The college library has a collection of 1,405 titles and 5,188 volumes. Out of 32 MSc passed out batch students, 12 students achieved university first ranks and 4 students obtained university second ranks. 2 students received Pratibha Awards. For the last 1 decade, more than 200 research papers were published in national and international journals. The major contribution has given by Dr. K.V. Acharya sir with 145 publications and Dr. N. Rafi sir with 65 research articles. That faculty members in the Department of Mathematics attended more than 150 faculty development programs or workshops, conferences, and seminars. Notable achievements are accomplished by the faculty members. In particular, Dr. K.V. Acharya sir created 3 unique world records in the field of mathematics research and honored with many awards and rewards. He authored 5 books and 10 chapters in various international publications. Dr. K.V. sir edited more than 150 books as editor-in-chief in various esteemed mathematical international journals. Faculty members in the Department of Mathematics completed 15 online NPTEL courses for enriching their knowledge. Among those completed courses, Dr. M. Balaya has completed 7. Last year, Department of Mathematics successfully organized an international faculty development program with 800 participants and an international workshop with 900 participants. This year also, we are conducting an international FDP with more than 800 participants and planning to conduct one international workshop in the month of December 2024 and one international conference in the month of February 2024. Now I come into FDP. On the first day, Dr. J. Bhaskar Babuji Garu, Professor, Department of Applied Sciences and Humanities, Anna University, MIT Campus, Chennai, has delivered a talk on graph techniques for cyber security. On the second day, that is yesterday, Dr. C. Pavan Kumar Garu, Faculty in Mathematics, Apex Max Excel Center, North Carolina, USA, delivered a talk on linear algebra tools and its applications. On the third day, Dr. K.V.V. Varprasad Garu, Assistant Professor, Department of Mathematics, Guru Gastha Viswavidyalaya, a Central University, Bilasapur, delivered a talk on iterative procedures for approximating fixed points of contra-type positive mappings. For the above 3 days, each session was engaged with more than 700 participants. Now I request one of our staff organizer, Ms. K. Sunita, to present the life sketch of Komaravalu Chandrasekharan Garu.
The short biodata of Professor Komaravalu Chandrasekhar includes with a heartfelt homage to his memory, celebrating his immense contributions to mathematics and his legacy as a visionary academic. It highlights his global influence, the pride he brought to his hometown of Bapatla, and his lasting impact on the field of mathematical research and education. The tribute recognizes his dedication, achievements, and the respect he garnered worldwide, offering a profound acknowledgement of his life's works and contributions. Early life and education. Born in 1920 in Machilipatnam, he studied in Bapatla and earned an MA in mathematics from Presidency College, Chennai. He pursued a PhD under Dr. K. Anand Rao, an associate of Srinivas Ramanujan. Career achievements are joined the Tata Institute of Fundamental Research at Homi Bhabha's invitation, establishing it as a global hub for mathematical excellence, played key roles in the International Mathematical Union and other prestigious organizations, edited the Journal of the Indian Mathematical Society. His research contributions are his work spanned fields like analytical number theory, Fourier transforms, elliptic functions, and topological groups. Awards and honors are recognized with the Padma Shri Award in 1959, Shanti Swarup Bhatnagar Award in 1963, and Ramanujan Medal in 1966. He became a fellow of the American Mathematical Society in 2012. Legacy, known for fostering mathematical research and publishing the Notebooks of Srinivas Ramanujan. He passed away in 2017 in Zurich. The biodata concludes with a heartfelt homage to his memory.
Thank you, Sunita. Now I request one of our staff organizers, Ms. I. Rajeswari, to present the life sketch of Dr. Nagala Prabhakar.
Brief biodata of Dr. N. Prabhakar Rao, ex-HOD, Professor, Department of Mathematics, BEC. Dr. Nagala Prabhakar Rao Garu, born on November 21, 1954, in Amrataluru, near Tenali, was a distinguished academic and visionary. A brilliant student, he pursued his passion for mathematics with a BSc and MSc in mathematics, culminating in a PhD in 1977 under Professor K.L.N. Swami Garu at Andhra University, renowned for his expertise in group theory, graph theory, and automatized algebra. He published numerous research papers in prestigious journals and collaborated with international scholars, including Professor Kiyoshi Iski of Japan. His contributions to Gris theorems in group theory were so groundbreaking that they influenced the name of Gris-Rao's algebra. Dr. NPS's teaching career began in 1977 at Siddhartha Engineering College. In 1983, he joined Bapatla Engineering College, serving over 3 decades in various roles, including HOD of Mathematics, founder HOD of Computer Science, and founder director of the Computer Center. He initiated innovative programs like BSc Computer Science and guided students to prestigious achievements, including placements and ISSC Bangalore. As an exceptional teacher and mentor, his passion extended to research. He established a university-recognized research center, supervised 12 MPhil and 3 PhD scholars, and initiated ideal departmental procedures that continue to guide faculty and students. Dr. NPS's legacy is marked by his profound impact on education and research at BEC. His dedication, innovation, and mentorship remain an inspiration to all. He passed away on December 30, 2023, leaving an enduring legacy of excellence. Thank you.
Thank you, Rajeshwari. Now, I humbly request our beloved head of the department, Dr. K.V. Nacharlu Garu, to give his valuable message on this memorable occasion.
Dear participants, today we have celebrated the birth anniversaries of 2 great individuals, Dr. K. Chandrasekharan Garu and Dr. Nagala Prabhakar Rao Garu, in the morning section at a GB conference hall. Both are from the soil of Bapatla and have made valuable contributions to the field of education and research. Before paying my homage to them, I would like to express my heartfelt gratitude On behalf of Maths Department, our magnanimous management and beloved principal, sir, for their constant encouragement and timely support in conducting various academic programs. Last year, we successfully organized one online international FDP with 800 participants and one online international workshop with 900 participants. I would also like to take this opportunity to thank all our faculty members for their cooperation. I strongly believe in Henry's Ford's proverb, coming together is the beginning, keeping together is progress, working together is success. The purpose of celebrating the birth anniversaries of great personalities is to honor their contributions, inspire future generations, and preserve their legacy, instill values, and promote academic heritage. Personally, I have learned so many things from Dr. Nagalla Prabhakar Rao Garu during my student life and in my teaching profession also. He is truly a role model for all of us, both as a dedicated teacher and as an eminent researcher. On the other hand, Professor Chandrasekharan Garu brought global recognition to Bapatla in the field of mathematics. His remarkable contributions to analytic number theory, Fourier transforms, elliptic functions, and topological groups. He has honored with prestigious awards like Padma Shri, Shanti Swarup Bhatnagar Award, and Ramanujan Medal, and a Fellow of American Mathematical Society. On behalf of Maths Department, I pay my heartfelt homage to Dr. Komarvolu Chandrasekharan Garu and Dr. Nagalla Prabhakar Rao Garu for their unforgettable services to the field of education. They have molded the lives of so many students by inspiring them with their dedication, knowledge, and passion for mathematics. Their contributions have not only enriched the academic world, but also set a shining example for all of us. Today, we have a wonderful resource person with us. The resource person for today's section is Dr. P.V. Sundaranand Garu, Professor, Head of the Department, Rayalaseema University, Kurnool. Dr. P.V. Sundaranand Garu is not only a professor, but also a source of inspiration, guidance, and support to the students' community. On behalf of Department of Mathematics, I express my gratitude to Dr. P.V. Sundaranand sir for graciously accepting our request to deliver his valuable lecture in our International Faculty Development Program. Thank you, sir. Thank you very much. Finally, I strongly believe that we will be enriched with the lecture given by our resource person for enhancing our knowledge on optimization problems in machine learning. Thank you, one and all. Thank you, sir. Karunakar, sir.
Okay, sir. Thank you, sir. Now I request one of our staff organizers, Ms. I. Rajeshwari, to present profound profile of Dr. P.V. Sundaranand Garu.
Good evening, everyone. I welcome you all to the one-week International Faculty Development Program on Innovative Applications of Mathematics. It is my honor to introduce today's resource person, Dr. P.V. Sundaranand Garu. Dr. P.V. Sundaranand Garu is a professor and head of the Department of Mathematics at Rayalaseema University, Kurnool. He has also served as Director of the Directorate of Admission, Dean of the College Development Council, Coordinator of HEPB, and registered at Rayalaseema University. Before joining Rayalaseema University, he worked as an associate professor at the C.R. Rao Advanced Institute of Mathematics, Statistics and Computer Science, University of Hyderabad. Dr. Sundaranand Garu did his MSc in Applied Mathematics from Andhra University in 1991 and his PhD in Applied Mathematics in 1997 under the supervision of Professor K.N. Murthy Garu. He received the Senior Research Fellowship from CSIR, India in 1994. Dr. Sundaranand Garu has published 32 research papers in national and international journals and 8 technical reports. He has also supervised students for their postgraduate and doctorate degrees. His areas of expertise include nonlinear dynamical systems, mathematical control theory, mathematical modeling, fuzzy control, computer science theory, and deep learning. He has worked on the design and analysis of indigenous ciphers, cryptanalysis tools using SAT solvers and SMT solvers, and test suites for evaluating the randomness of bit-based and word-based streams. He has provided consultancy of standard and post capital IQ and GEM lubricants, delivering Excel models for random sample extractions, sample size determinations, and model validation using Excel VBA to improve product and employee quality. Dr. Sundaranand Garu is respected for his exceptional teaching methods and research contributions over the past 30 years. His approachable nature, positive attitude, and expertise make him a valuable resource to the academic community. Thank you.
Okay, thank you, Rajeshwari.
Karnakar sir, your voice is not audible, sir. Please check it.
Now I hand over the session to Dr. P.V. Sundarananda sir. Sir, please start the session, sir.
Yeah.
Sir, is it audible?
Yeah. Am I audible?
Yes, sir. Very clear, sir.
Sir, what about my presentation? Is it seen?
No, sir.
Okay. Let me try again. Okay. So, share. Sir, is it seen?
Yes, sir.
Yeah. So, good afternoon to everybody. At the outset, I would like to thank Dr. T. Srinivas Garu for giving me the opportunity to share this afternoon with you all. I would also like to thank Dr. Acharyul Garu and former friend and Dr. Karunakar Garu. My association with them goes back to 1996. I'm also thankful to Dr. Rajeshwari Garu for her kind introduction. And so when I was asked to deliver a talk in this session, I have chosen optimization problems in machine learning. And my pranams to Komarvoli Chandrasekharan, a legend. Actually, all over previously his entire biodata was introduced, and he is the founding member of IAM India. Besides, he received Bhatnagar Award, Ramanujan Medal, and many more. And after that, he moved to Zurich. And Komarveli Chandrasekharan's famous students are C.S. Sheshadri and Narasimhan. And both Seshadri and Narasimhan sir contributed immensely to the mathematics field, not only in India, at a global level. And my pranams to Dr. Nagala Prabhakar Rao Garu. I know him because myself and Prabhakar Rao Garu joined our careers in VR Siddhartha Engineering College. And not only that, I met him a couple of times when I visited Babatla Engineering College. And he was quite friendly, cordial, and he, as it was told, his contribution to the field of mathematics is immense. And let me start with the famous saying of Pascal. If I had more time, I would have written you a shorter letter. So with this saying, we can understand, the importance of optimization. What is optimization? Let us start with a small problem. A farmer has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs to fence along the river. What are the dimensions of the field that has the largest area. It looks like, you know that one side river is there, for that fence is not required. And if you take 100 and 2200, area is 2,20,000. And if you really take 700,000, you can have 700,000 is the area. If you take some other dimensions, it is changing. Okay. The question is, we need to maximize the area. So area is x into y. Constraint is nothing but 2x plus y equal to 2400. Solution is a is equal to 720,000. Whenever you take x is equal to 600, y is equal to 1200. It is a maximum area. So optimization, whenever we talk from higher secondary level, we have been dealing with optimization, either maximization or minimization. But we are more interested in constraint optimization. You cannot really go for optimization without any constraint. In a real world scenario, you are going to have many constraints. So, you know that we can have a stationary point and you can have a point of inflection. Function is going to take, here it is maximum, here it is minimum, here it is a point of inflection. All of us know that at the first derivative should be equal to 0 for extreme case. So, but the main issue nowadays is going to be global optimization or local optimization. So it's all about moving to global from local. That is the basic idea. So you know that if you really look at this is the local minimum, but whereas global minimum is here. Unless or otherwise you surf around, you go beyond and you try to really look at the horizons of the issue, you cannot really go to the global minimum or global maximum. And who are the contributors for optimization? Isaac Newton, development of differential calculus, methods for optimization, and Lagrange, calculus of variations, minimization of functionals, method of optimization for constraint problems, and Cauchy, and solution by direct substitution, steepest descent method for unconstrained optimization, and Euler, once again he contributed through calculus of variations, minimization of functionals, and Leibniz. And because of Leibniz, we are having differential calculus methods for optimization. And Danzy, George Bernard Danzy, who is really contributed in the form of simplex method, especially in alien programming. Then in the recent past, we are having Richard Bellman, principle of optimality in dynamic programming problems, and Harold William Kuhn. And we know about Kuhn-Tucker methods. And Kuhn as well as Tucker, they really contributed in the nonlinear programming and optimization. Of course, we should not forget the von Neumann, whose contribution is immense in game theory. And optimization, if you really look at some of the popular algorithms which people have been using, and deterministic algorithms, and Monte Carlo algorithms, evolutionary computation, and meta-heuristic algorithms, and nature-inspired like swarm intelligence. In the swarm intelligence, you can have particle swarm optimization and colony optimization, and firefly optimization, BAT algorithms. In the bio-inspired and a finite field algorithm, artificial immune network, so on and so forth. So when we talk about machine learning, the first question that will come to our mind is human beings can think. No doubt about it. All of us are human beings. We are capable of thinking. We do think. Now the question is, can computers think? If computers start thinking, what about the relationship between thinking capacity of a computer and that of the human being? Are they equal? Approximately equal? Not equal. We can say that their thinking capacity of a computer is always less than that of a human being. And what is artificial intelligence? You know, computers making decisions in the real world problems. The idea is you can formulate, you can solve, you can apply, you can take feedback and keep on improving it. And in the artificial intelligence is going to have expert systems, speech recognition, case-based reasoning, neural networks, natural language processing, soft computing, intelligent agents. You know, in all those areas, we are going to have learning, reasoning, problem solving, perception, language understanding. They are going to play a vital role. So AI means it is going to have all of them. And how speech recognition is going to work. So we can give voice input. So it will be in the analog form. Analog signal will be converted into a digital signal. Then you can have acoustic model. Then you can have a language model. Then it will be fed to the speech engine. Then it is going to display what it is. You can take feedback and goes back. And depending upon the feedback mechanism, we can improve the speech recognition. You know, articulation produces sound waves, which the ear conveys to the brain for processing. As is done in the human beings, machines also do the same thing. And you can have acoustic waveform or acoustic signal. You are going to digitize it, and you can do acoustic analysis, and you can do the linguistic interpretation. Okay. My number is 7390274. Okay. So what is digitization? Converting analog to digital. What is signal processing? Separating speech from background noise. What are phonetics? Variability in human speech. And human speech naturally people classify it by using frequency as well as some other characteristics. And phonology, recognizing individual sound distinctions, is the systematic use of sound to encode meaning in any spoken human language. Next is lexicology and syntax. And what is process of speech recognition and speaker recognition? Suppose in the previously we were having with Bharati All India Radio, and who is speaking and what is he saying and what is he talking about? There you can have parsing and arbitration. And that's how you can really infer who is speaking, what he is speaking, and thereby you are able to really understand. That is simply what is speech recognition means. And expert systems, they model human knowledge as a set of rules that are collectively called the knowledge base. And rules may be any from 200, 300, 10,000 or 1 lakh, depending upon the complexity of the problem. And the system's inference engine searches through the rules and fires those rules that are triggered by facts gathered and entered by the user. And useful for dealing with problems of classification in which there are relatively few alternative outcomes and in which these possible outcomes are all known in advance. And we are having a non-expert user, we are having an expert system, and in that user interface is there, inference engine is there, knowledge base is there, but the contribution of expert is much more in this. And expert system is having the following components. Knowledge acquisition subsystem, which is going to have knowledge base, inference engine, user interface, and you can have a blackboard, also known as workplace, and explanation subsystems, they are justifiers, knowledge refining system, users, and most of the expert systems do not have a knowledge refinement. That is a major issue. And you can have explanation facility, inference engine, knowledge base, and knowledge base acquisition, user interface. There is a two-way communication between experts and users. And broadly speaking, you can have a domain expert, you can have a knowledge engineer, and finally, the client or the knowledge user. And expert systems development, it is determining requirements, identifying experts, construct expert system components, implementing results, maintaining and reviewing systems. And the domain expertise is mandatory. Can explain the reasoning or suggested decisions, display intelligent behavior, draw conclusions from complex relationships, and they provide a portable knowledge. And a collection of software packages and tools used to develop expert systems. So expert systems, you can have rule-based expert systems, frame-based expert system, neural expert systems, fuzzy expert system, neuro-fuzzy expert system. What are their applications? Information management, hospitals and medical facilities, help desk, employee performance evaluation, loan analysis, virus detection, repair and maintenance of projects, warehouse optimization. What are the limitations of expert systems? They are not widely used or tested, limited to relatively narrow problems, cannot readily deal with mixed knowledge. There is a possibility of error, and refinement is not always possible, so easy, not implementable. And maintenance issues are there, and development costs are much more, and they may really raise legal or ethical concerns. Then is NLP, popularly known as NLP, natural language processing. So all of us use some language or the other to express ourselves, to communicate. But the thing is, two human beings can converse if they have a common language. Similarly, if you want to converse with a machine, especially a computer, you need this NLP. So there won't be any computer mistakes. There will only be a mistakes by the human being. How you instruct, a machine is going to perform. So taking some spoken or typed sentences and working out what it means. And today we are having Google, and from the Google there are many engines which are giving us translations. Okay, and understanding not only in one language, many other languages, and taking some formal representation of what you want to say and working out a way to express it in a natural language. Most of it is going to be English. It is an amalgamation of linguistics, philosophy, computer science, and psychology. All of them put together are going to make a natural language processing. And in the NLP, you need to map them. So mapping the given input in a natural language into useful representation. And most of the times, whenever we talk about any language, we need to encounter popular problem of ambiguity. The same sentence is going to have many meanings. The same word is going to have many meanings. Or a word is going, the meaning of the word, is it going to change with that of the context? And the meaning of a word, is it going to depending upon its predecessor and follower? So naturally ambiguity is to be addressed. So there are, you can classify the ambiguity: lexical ambiguity, syntax level ambiguity, referential ambiguity. Okay. And in the NLP or natural language generation, you need to have text planning, sentence planning, text realization. These are the basic steps that are involved. What is lexical analysis? Identifying and analyzing the structures of words, collection of words and phrases, dividing the whole chunk of text into paragraphs, sentences, and words. Next is syntactic analysis. So it is analysis of the words in the sentence for grammar, arranging words in a manner that shows the relationship among the words. So grammar is basically to uh, resolve the ambiguity or to fix meaning. So another is semantic analysis, checked for meaningfulness and mapping syntactic structures and objects in the task domain. Another is discourse degradation. Any sentence depends on meaning of the sentence just before it and immediately succeeding sentence. Another is pragmatic analysis. What was said is reinterpreted on what it actually meant, deriving those aspects of language which require real world knowledge. So we really want to have a C of Z, context free grammar, which is a top down parser. And you can have articles, nouns, noun phrases, verbs, verb phrases, adjectives, so on and so forth. So suppose you are given a sentence, the bird pecks the grains. If you want a machine to understand the meaning of this particular sentence, what is you need to really divide the entire sentences into words and what are the meanings of those words. And depending upon its predecessor and follower, the meaning of the word may really change. You need to do some sort of a classification. You know, what is the and what is bird, pecks, the, grains, which is noun, which is adjective, which is verb. Here we are going to use top-down parser. Parser starts with a S symbol and attempts to rewrite it into sequence of terminal symbols that matches the classes of the words in the input sentences until it consists entirely of terminal symbols. These are then checked with the input sentence to see if it matched. If not, the process is started over again with a different set of rules. This is repeated until a specific rule is found which describes the structure of the sentence. Simple to implement, slow, inefficient, as a such process has to be repeated if an error really occurs. Okay. So what are the uses? And close words that aren't phrases, distinct words that are phrases. And it is the main issue using NLP. And terms co-occurring more often than chance. Within small number of words, surrounding simple terms, not surrounding punctuation. Okay. And parsing for phrases. Whenever there is an ambiguity, you have to really remove it. Disambiguation is to be done. Automatic analysis of these 4 scientific tests. So, automatic is adjective, analysis is noun, off is a preposition. These 4 scientific, etc., they can be classified. Okay. And where is the optimization? Optimization of NLP components for robustness and scalability, graph models and optimization in natural language processing. And next is soft computing. And soft computing is a coalition of methodologies which collectively constitute a system with wide-ranging capabilities of the conception, design, and operation of intelligent systems. So better results can be achieved through the use of constituent methodologies of soft computing in combination rather than isolation. So whenever we talk about fuzzy logic, we should remember Jade is a mathematician, electrical engineer, computer scientist, artificial intelligence researcher, so on and so forth. And what is soft computing components? There is a fuzzy logic, neural network, artificial immune networks, reinforcement learning, probabilistic learning, machine learning, evolutionary algorithms based on the origin of species, swarm intelligence. In the evolutionary computation, we are having first generation, second generation, third generation. And they are all inspired by some of the, either from life science problems or genetic algorithms or mutation of genes or from the nature like ants or bats. And you can do these type of algorithms, swarm intelligence. I don't want to really read out all of them. Okay. So let me really tell you about Goldbach conjecture. Every even integer greater than 2 can be expressed as the sum of 2 primes. That is a big number, is the smallest number that has no Goldbach partition with a prime below 9781. It is a unique prime factorization theorem. Every integer greater than 1 either is prime itself or is the product of prime numbers, and that this product is unique up to the order of the factors. So discovery, when we talk about discovery, this can also be considered as a great discovery. Okay, how can we teach things to computers? In order for a program to be capable of learning something, it must first be capable of being told it. It was told by none other than John McCarthy. So the brain versus computer. No, brain is having 10 billion neurons, 60 trillion synapses, distributed processing, nonlinear processing, parallel processing, all those things human beings do have. And if you really look at a computer, and faster than neuron and central processing, arithmetic operations, sequential processing in a machine. In the artificial neural network, what are neural networks? Models of the brain and nervous system. They are highly parallel, process information much more like the brain than a serial computer. It depends upon a simple principle, but behaviors are complex, and it is a powerful problem solver inspired by the biological models. So broadly speaking, you can give inputs. You are going to have weights and you can add some bias and will be getting the output. And being a student of math, I really look at this as function of some quantity. P1, W1, P2, W2, P3, W3 plus B. There's a bias. Weights, they keep changing. And whenever we start working in neural network, there is a feed forward neural network. What is feed forward? Flowing of data from input layer to reach the output layer after getting processed in hidden layer is called feed forward. Till now, I have not presented what are layers. Okay, of course, I'll be showing them after 1 or 2 slides. Another is back propagation. It is going to calculate the error at output layer and propagate it back to edit the bytes and bias to minimize the error. We are having 5 steps. You are going to initialize with weights and bias for each neuron, and you can have a feed forward information of input to the hidden layers and then to the output layer. Third step, SSS, the error output of the network on the known output. Fourth step, propagate the error backward to adjust the weights. Adjust the weights using gradients of change to reduce the errors. So all of us are nowadays using computers, and we in a neural network scenario, we are going to have epoch, and in a numerical analysis scenario in mathematics, we do have iterations. What is the basic difference between them? What is epoch? An epoch describes the numbers of times the algorithm sees the entire data set. So each time the algorithm has seen all samples in the data set, an epoch has been completed. Iteration. An iteration describes the number of times a batch of data passed through the algorithm. In the case of neural networks, that means the forward pass and backward pass. So every time you pass a batch of data through the neural network, you completed an iteration. The basic difference between epoch and iteration is that, say you have a data set of 10 examples or even 10 samples. You have a batch size of 2 and you have specified you want the algorithm to run for 3 epochs. Therefore, in each epoch, you have 5 batches because you are having 10 samples and you are having only 2 batches. 10 by 2 is 5. Each batch gets passed through the algorithm. Therefore, you have 5 iterations per epoch. Since you have specified 3 epochs, you have a total of 15 iterations per the training. What is optimization in back propagation? Gradient descent, Cauchy-Newton back propagation, Brodin, Fletcher, Goldfrapp, and Shannon, Newton's method. In the gradient descent, conjugate gradient descent back propagation with the momentum, the Pollock-Ribéry conjugate gradient descent. Suppose you are having neurons, nearly 86 billion nerve cells connected to each other, 1,000 cells by axons. Stimuli from external environment or inputs from sensory organs are accepted by dendrites. These inputs create electric impulses which quickly travel through the neural network. A neuron can then send the message to other neuron to handle the issue or does not send it forward. And let me start. What is a neural network? It is going to have nodes. Nodes imitate biological neurons of human brain. The neurons are connected by links and they interact with each other. The nodes can take input data and perform simple operations on the data. The result of these operations is passed to other neurons. The output at each node is called its activation or node value. Each link is associated with a weight. Artificial neural networks are capable of learning, which takes place by altering weight values. Look at artificial neurons. You are having inputs x1, x2, x3, xn. You are assigning weights w1, w2, w3, wn. Corresponding to each input, you are assigning a weight. Thereby, you are getting z is equal to w1 x1 plus w2 x2, so on wn xn. This is your z. It's a linear sum. And you are defining a function of z, h of z. And it is going to give you the output. It is a Macaulay-Pitts model. Feed forward ANN. It is unidirectional, no feedback loops, fixed inputs and outputs, pattern generation, recognition, and classification. They are all feed forward. You can say it is only one direction. And another is feedback ANN. You know that from this you are coming back. Again, weights are adjusted. And fully recurrent network. You know, there is a two-way classification, two-way communication. It is a fully recurrent network. And another is a closed loop network in which the output will go to the input again as a feedback. It is in the Jordan network. These are the inputs, these are the hidden ones, these are the outputs, and they are going back. And thereby, you are having this Jordan network. If the network generates a good or desired output, there is no need to adjust the weights, but it is an ideal scenario. In general, it won't happen at all. If the network generates a poor or undesired output or an error, then the system alters the weights in order to improve subsequent results. But the second one is going to happen most of the times. Machine learning in artificial neural network. And you can have supervised learning, unsupervised learning, reinforcement learning, backpropagation learning. What is supervised learning? Example is the pattern recognition. Or we can really think of using a numerical method. You can solve a differential equation. You can fix solutions as target, and you can do supervised learning, and you can construct an artificial neural network. Unsupervised learning. Searching for a hidden pattern. Most of the times we use energy functions here because we don't have any guess or some estimate about our solution. Another is reinforcement learning. This strategy built on observation. The ANN makes a decision by observing its environment. If the observation is negative, the network adjusts its weights to be able to make a different required decision in the next time. Another is backpropagation algorithm. Here you can have training or learning, or training and learning, both will happen. And learns by example. Changes the network's weights so that it can produce desired output for a particular input on finishing the training. So simple pattern recognition and mapping tasks. From biological neuron to artificial neuron. Okay. If you really look at it, dendrite, you can have a synaptic weights. Cell body, you can have a threshold. Axon, you can have an output. Okay. So whenever we talk about this artificial neurons, it is nothing but a non-linear generalization of a Macaulay-Pitts neuron. Y is equal to f of x comma w. X is the input, w is the weight. You know what this function is going to be. Linear functions may not represent many real-world scenarios. So that's the reason why we always take non-linear models. So Y is the neuron's output, X is the vector of inputs, W is the vector of synaptic weights. So if I take a sigmoidal neuron, the function f of xw is defined as 1 by 1 plus e to the power of minus w transpose x minus a. Similarly, you can have a Gaussian neuron inspired by a normal distribution. What are properties of artificial neural networks? And it is a multi-layer perceptron network. What are the characteristics? Nonlinear input-output mapping, adaptivity, generalization ability, fault tolerance, and biological analogy. So you know that input layer, first hidden layer, second hidden layer, output layer. So I represented two hidden layers. Not necessary that we can have two hidden layers. You can have 3, 4, 5, so on and so forth. What are the types of ANNs? Single layer perceptron, multi-layer perceptrons, radial basis function networks, Hopfield network, Boltzmann machine, self-organization map, modular networks. What is a single layer perceptron architecture? So we consider the architecture. We are having a feed-forward neural network with one layer. It is sufficient to study single layer perceptron with just one neuron. So uses a nonlinear model, neuron x1, x2, w1, w2, wm, and you are adding a bias b, and combining all of them, you are going to have v, then phi of v, then your output. Here phi is the sine function. Phi of v is equal to 1, v is greater than or equal to 0, phi of v is equal to minus 1, v is less than 0. What are the applications? The perceptron is used for classification. Classify correctly a set of examples into one of the two classes, say C1 and C2. If the output of the perceptron is +1, then the input is assigned to class 1, C1. If it is -1, you can assign it to class 2. So the equation below describes a hyperplane in the input space. Okay, this is the decision boundary. W1 x1 plus W2 x2 plus B is greater than 0. Above the line, you are having one class. Below the line, you are having another class. And along the line, you are having 0. If it is greater than 0, green dots, less than 0, black dots, and equal to 0, it is your decision boundary, it is a line or a plane. So multi-layer perceptron network, and you can have a whole field network. You can have corresponding weights you can assign. From single layer to multi-layer perceptron. So input, I'm having 3 hidden layers, then I'm having a output. You can understand that I'm increasing the hidden layers. What are the properties and the architecture? No connections within a layer, no direct connections between input and output layer, fully connected between the layers, often more than 3 layers. Number of output units need not be equal to number of inputs. Number of hidden units per layer can be more or less than input or output unit. You know, neurons, you can also increase neurons. Okay. And you can include bias as an extra weight also. And back propagation has 2 phases. Forward fast phase. A computer's functional signal feed forward propagation of input pattern signals through network. Backward pass phase. Computer's error signal propagates the error backwards through network starting at output units, where the error is the difference between actual and desired the output value. It is described. This is the forward, input to output, backward is from output to input. Conceptually, forward activity minus backward error. Okay. What are the features of artificial neural networks? Records, they are known as examples, need to be represented as a set of tuples. You can have an attribute and you can have a value. The output values can be represented as a discrete value, a real value, or a vector, or anything at all. Tolerant to noise in input data. Time factor, it takes long time for training. Once trained, an ANN produces output values very fast. It is hard for a human to interpret the process of prediction by ANN. Let me tell you about genetic algorithm proposed by John Henry Holland, a class of computerized search and optimization algorithm adopted from process of natural genetics, natural selection and evolution. And here the crux is selection, crossover and mutation. Those 3 are going to be vital. In the genetic algorithm, in the first stage, selection better chromosomes and with the help of an operator. The crossover operator typically combines 2 different parents to produce new chromosomes, and in order to inject diversity into the solution and avoiding it to be trapped inside a local maxima or minima, the mutation operation is used. Look at chaotic particle swarm optimization. It is going to mimic swarm of birds flying behavior and utilizes its ability to find a solution. Each particle in PS4 denotes one bird, and each particle is assigned an initial location and velocity. According to the best particle, the best location, the particles constantly updates its velocity and location. In the basic PS4, the optimization approach employs the global best of the particle as a neighborhood topology. Each particle learns from its previous best PI and go global PG. The chaotic PS4 employs chaotic perturbations on best G to update the particle position. This chaotic perturbation helps in avoiding premature convergence and enables the algorithm to find global optimization solutions. The updation of each particle is also influenced by its own best position. its previous velocity and global best position among all the particles. Next is differential evaluation. It is by Kenneth P. Price and Rainier Strom. Differential evolution is one of the evolution algorithm that is used for global optimization over a continuous search space proposed by Storm and Price. Three operators, namely mutation, crossover, selection, defines the operation in DE. The DE population evolves through repeated cycles of these three main operations. The process can be summarized as mutation of three randomly selected vectors, creating a final vector by crossover of mutant vector and target vector. Unlike the genetic algorithm, where parents are selected based on fitness, every solution differential evaluation takes turn to bear target vector. Thus, all the vectors play a role as one of the parents with certainty. And this ensures diversity and reduces the chance of good solution being eliminated. Then you can have Hopfield networks. It is composed of binary threshold units with recurrent connections between them. Recurrent networks of nonlinear units, they are generally very hard to analyze. They can behave in many different ways. They can settle to a stable state. Sometimes they oscillate, follow chaotic trajectories that cannot be predicted far into the future. All the nodes in a Hopfield network are both inputs as well as outputs, and they are fully interconnected. But Hopfield realized that if the connections are symmetric, there is a global energy function. Each configuration of the network has an energy. The binary threshold decision rule causes the network to settle to the energy minimum. Now, we are coming to one of the important concept called gradient descent algorithm. What is the architecture of a perceptron? You can have input, weights, and you are having a function, activation function. Input a vector of real values. Your output is going to be 1 or -1. It is a binary one. And an activation function, it is a threshold function. And we are quite aware of LMS, least mean square error. So consider a simple linear unit where W0 plus W1 x1 Wn x1 is your output. Let's learn WIs that minimize the squared error. So idea is we need to improve weights. We need to compute weights. We need to update weights. We need to modify weights. We need to change weights. What for? We do all those things to minimize the error. What is the error? Error is given by TD minus body square. It is a squared error so that you can nullify the sign. Where D is set of training examples. Output value O is a real value. It is not binary. And delta rule. Learning rule for an unthresholded perceptron. Delta rule is a gradient descent rule, also known as Wedlow-Hoff rules. Look at the gradient descent method. I am taking nabla E of W bar is dou by dou W naught of E, dou by dou W1 of E, dou by dou W1 of E. So training rule is what? Delta W bar is equal to minus theta nabla E of W bar. From this, delta Wi is given by minus theta dou by dou Wi of E. Corresponding to each weight, you can have this. You know, this is the gradient. Idea is it is decreasing. Okay, you want it to decrease. What is the delta rule for error minimization? So as we know from the basics of mathematics that if you are having a function of more than one variable, so you need to take their partial derivatives with respect to each variable and equate it to 0 and see that at those points you can test for direction. Is it going upward or downwards, or it's a maximum or minimum? And dou E by dou Wi is E is nothing but TD minus body whole square summation. And simple mathematics is going to yield dou dou W of E is TD minus body into minus XI into D. So from this, delta Wi is given by eta into sigma of TD minus body XID. Okay, it is adjusted here. What are the limitations of gradient descent? Converging to a local minimum can sometimes be quite slow. Many thousands of gradient descent steps. So it is going to affect the complexity of the algorithm and complexity. If there are multiple local minima in the error surface, then there is no guarantee that the procedure will find the global minimum. It will be oscillating. It will be going from one local minima to another local minima. But will it really reach the global minima is a question mark. In the case of large number of hidden layers, this gradient descent fails to update the weights at the lower layers, which is known as vanishing gradient. You know that whenever complexity of the problem increases or difficulty, my complexity is not going to deal with the time taken for the algorithm to execute. Okay. If the difficulty of the problem is there, so naturally you keep on increasing more number of hidden layers. And if you really look at the principles of computation, we talk about a basic machine, finite state machine, Turing machine, then Turing machine with memory, halting problem is going to be, then your computer will be coming. See the mathematicians basic machine as a function of one variable and finite state machine as function of two variables. Why it came FSM? Because to handle the problem of carryover bit. Okay. Then you can have only one direction. Then you can have a Turing machine, and control can go both way, but somewhere it should stop. Okay. If you are having a difficult problem, you are increasing the number of states. Number of states is not going to resolve the problem. You need a ideal state where you really optimize it. We are having Karnoff map, Quinn-Minkowski algorithm, etc. to have that optimization level. Either for computer science people or math people are quite aware of it, the minimization of Boolean functions. Okay. Now, here we are into vanishing gradient. Why I brought that similarity is here you keep on increasing the hidden layers so that you want to really train it in an efficient manner. So, what happens whenever you increase the hidden layers? So, whenever you are changing the weights, the initial layers may not get proper input or may not get proper updation. So that is your vanishing gradient issue. So solution is RBM. The problem of exploding the vanishing gradients, what happens to the magnitude of the gradients as we back propagates through many layers? If the weights are small, the gradient shrinks exponentially. If the weights are big, gradients grow exponentially. Typically, feed-forward neural networks can cope with these exponential effects because they only have few hidden layers. Understand? Few hidden layers. Even with good initial weights, it's very hard to detect that the current target output depends on an input from many time steps ago. So RNNs have difficulty dealing with long-range dependencies. In the case of large numbers of hidden layers, gradient descent fails to update the weights at the lower layers. Why the back propagated gradient blows up? If we start a trajectory within an attractor, small changes in where we start make no difference to where we end up. But if we start almost exactly on the boundary, tiny changes can make a huge difference. So, you know that vanishing gradients is an issue. So, let us do some practical issues. In logistic regression, if I am having y is equal to w dash x plus b is not used because given x, we want output to be the probability of y is equal to 1. So our output must be between 0 and 1 so that we use a nonlinear function. Linear function will be of no utility. Don't be confused that neural networks are used only for classification problems, which is wrong. Neural nets are used to regression problems, but the thing to do is just don't use any activation function at the end or output layer. And using linear activation functions in neural networks doesn't find any complex patterns, but simply acts as a linear regression model. Here, I would like to insist on the nonlinearity importance of nonlinearity. Okay. What are activation functions? ReLU. What is ReLU? Rectified linear unit is better used as activation function than sigmoid or tan h because in other two functions the slope tends to 0, which makes gradient descent tough to learn parameters. Even though ReLU's half range is 0 itself, but generally z will be positive in practice, which brings g of z. That is, g is a ReLU function. It will make it positive, and due to slope variation, parameters are learned, and we got the best. So ReLU will be of some utility. Sigmoid function is used only for binary classification, 0 or 1. And even when compared to sigmoid, tan h is pretty good because of its steepy nature. So gradients are more non-zero. So what we are trying to do, we arrived at what is known as gradient descent and how to handle gradient descent. That's what we are doing. Linear functions are not used as activation functions. If linear function is used in hidden layer and sigmoid latter, then we can simply say that hidden layer is useless because to bring complex features, we need a nonlinear function. We use nonlinear functions as activation functions in neural networks. Why only back propagation? Instead of back propagation or gradient descent, we can also just take the derivative of the loss function with respect to input and equate it to 0 so that weights can be found. But this is not preferred because derivatives of loss function in neural networks is not closed form. That is, we need to perform differentiation more than once to make it 0. Initializing weights of neural networks. Practically, how to initialize weights? And weights can be initialized by 0, and sometimes 0 is not preferred. This causes all the neurons or units in the layer to be same for every iteration in gradient descent. So we initialize randomly, and we should be sure that the initializations should be very small. If they are large, then after applying activation functions on them, gradient descent doesn't change the parameter much in sigmoid and tan h. In neural nets, hyperparameters. What are the hyperparameters? Number of layers, hidden units, learning rates. These are the ones which control parameters. Parameters means weights and biases. If the data given is not large enough, then dividing it into train, cross validation, test sets, you can use this ratio. 60, 20, 20 is fine. But when there is a huge data, 98, you need to train 2 cross validation and 1 test, or 99.5 train and 0.4 cross validation, 1 will be okay. These are the practical issues which I would like to discuss. And though we talk about some of the theoretical limitations, relevance, but practically we need them. And what is a dropout regularization? What we do is we take one training example and toss a coin. That is, we'll make some probability in keeping and eliminating nodes, and keep some nodes in the neural network and shut the others, and again for the other example toss a coin, eliminate the nodes, and do this for all examples. The idea behind this particular paragraph is you need to incorporate randomness. You cannot really be choosy. You cannot have any bias. You should be unbiased. If you incorporate randomness, there is every chance that you can get better results. And similarly, if you use nonlinearity, there is a chance that you can get better results. And inverted dropout is one of the techniques in implementing dropout. What happens there is, let us talk about a network and assume we are on layer 3. First step, let D3 be a vector where D3 is equal to np.random.rand, and that is, we made a D3 matrix which has same dimension as a 3 matrix or a vector. Okay, and keep probability that decides how much percentage of value in D3 should be 0. Okay, suppose you really want it to be 80%. It means that 80% of the value should be there and 20% chance of eliminating units. Okay, so in a total, you would like to eliminate 20%. So the question is, which are to be eliminated? So D3 is a matrix where 20% values are 0 and remaining are 1. Step 2, we multiply A3 by D3, of course element wise. So 20% units naturally become 0. Step 3, you will be getting the probability. And what is the explanation for step 3? Let there be 50 units in the third layer. So your key probability is 0.8. Key probability is nothing but you would like to keep 80% and you would like to throw remaining 20%. So now 10 units in the third layer are eliminated because 20% of 50 is 10. Now when Z4 is calculated, Z4 is equal to W4 A3 plus B4 as 20% values in A3 become 0 and Z4 values become less than the expected 1 to neutralize it. So A3 will become A3 over 0.8, which is going to balance your Z4. The units eliminated will be changed in every iteration of gradient descent. Dropout is to be implemented only on training set. Since regularization is applied only in training set, it is not needed in applying per test set. If applied so, it acts like a noise. What is a dropout intuition? Cannot rely on one feature. So spread the weights. You are calling it as Hx is equal to W1 x1, W2 x2, so on. W1, W2, they are all weights. Either they grow exponentially or they shrink. Okay. So shrink the square norm of the weights, like L2 regularization. I think all of you know about L2 norm. As in dropout, each time different units disappear, so the resultant unit doesn't exactly rely on one feature more, but instead it is vulnerable to all others equally, which leads to shrinking of weights. What is normalization? For normalization, we calculate variance of the data and then perform X. So all the features in X have the same variance. Data varies equally among the features. So why we really require normalization? Because when we call cost function, the contour will be like elliptical. So then gradient descent have to take more steps and oscillate to and fro, to reach the minimum. Whereas when we normalize, we divide the data points by variance, which makes the distribution same for all features. So the contour almost will be symmetric. And gradient descent, we can take larger steps and need not even oscillate and reach the minima quickly. That is, it will be easy to optimize the cost function when features are on similar scale. I'm jumping to deep nets. I started working in neural networks way back in 2000. From 2009 onwards, I am working in neural networks. In the initial stages, we were using supervised networks. Then we were using energy functions for unsupervised networks. Nowadays, we are using deep networks. Okay. And what are the issues in the deep nets? When we initialize the weights slightly greater than 1, what happens is with increase in number of layers, the activations increase exponentially in L. L is number of layers. So more than the number of layers, higher the values of activations, which follows more the values of the gradients, which makes large steps. Then similarly, if weights are slightly less than 1, then the activation values gets vanished and gradients get lessened, which makes the steps in gradient descent very small and takes more time. Then solution to the, what is the solution to the above problem? So there are two issues. Weights are large, one problem. Weights are small, another problem. So how to handle it? One of the solution is to initialize weights carefully. When the activation function used is ReLU, then the weights initialized as using this square root of this function you can use np dot square root of this. Okay, this does not solve the problem entirely, but reduces to a good extent. I'm not recommending that it is the solution, ultimate solution. Definitely, it will make our life a bit better. Okay. Next, mini batch gradient descent. It is used when big data is used. In mini batch, what happens is, as we will divide the training examples into batches, the graph when plotted between the number of iterations on the x-axis and cost on the y-axis, and there will be noise like increasing and decreasing, but finally the trend will be like decreasing, but with some noise, which does not happen with a normal or batch gradient descent. It will have a smooth curve. The noise in mini batch is due to first mini batch may have higher cost, and second mini batch may have lower cost, and third higher and lower. But with the number of iterations, what happens? The whole curve gets decreased with the noise itself. Another is moving average. If you are having a little bit of knowledge about time series. We are having moving average method. Okay. ARMA, ARIMA, autoregressive models, moving average. It is nothing but it is a common sense. Given a data set of moving average of all previous points plus new point divided by number of points. It is average. So when the given data set is noisy, plotting moving averages decreases the noise and the line will become a bit smoother. And exponential weighted moving average or exponential weighted average. It is similar to moving average, but here average is not simply the sum of points, but it is the weighted sum of the points. Expression is given by this. Okay. From this expression, we say that BT as approximately as computing the average of 1 by 1 minus beta data points. Beta is a factor which decides the smoothness of the curve. More the value of beta, more smoother the curve. So when gradient descent is used, it takes many oscillations to converge. But when exponential weighted average is used on it, then the oscillations during convergence gets reduced so that minimum will be reached faster. Here we are concentrating on rate of convergence. Here what is the math? VDW is beta VDW plus 1 minus beta into DW. VDB is equal to beta VDB plus 1 minus beta DB. W is this. B is equal to B minus. Instead of DW, DB, we are here using BDW and BD. A simple formula. RMS prop is root mean square prop. It is similar to EWA, but equations are as below. Okay. The epsilon is very small quantity which ensures denominator to not to be 0. Okay. Here you are having square root of SDW plus epsilon, and epsilon is a very small, but it's not 0. And then you can have adaptive moment estimation. And this is a optimization algorithm. This is a combination of EWA and RMS optimization algorithm. Math is I am taking those two and thereby able to really. So what I mean to say is there are many available tools, many available functions, many available optimization algorithms. It is up to you to use them in a combination. Okay. Next is batch normalization. In neural networks, what we have done till now is just normalized input values, but not the activations. Those we get after each neuron, it is important to normalize those values. So to normalize those, we use batch normalization. So mean is equal to 1 by m sum of x, mean variance. We use all these formulas, okay, for the batch normalization. And covariant shift. The change of distribution of data, not values but whole data, so is the problem, is called the covariant shift. Due to this change, the results we get might not be true. To reduce this problem, we use batch norm, which keep the distribution same. That is, mean and variance same, no matter how much change there is in the values. Don't use batch norm as a regularization technique. Instead, just use it as a normalization technique, which speeds up the algorithm. But regularization is just a side effect of it. For batch norm, we take mini batches as input in training set. But in general, we will not have much data in test set So we are forced to take one point at a time. Test data, we cannot So what we do is for test set, we will take mean and variance, which are the exponential weighted averages, and all the means of many batches calculated in training, and use those mu and sigma, mean and standard deviation values in the test set. Okay. In the training, you can use mean 1 variance 1, mean 2 variance 2, mean 3 variance 3, third mini batch. And each batch is going to have its own mean and variance. So what we do is calculate exponential weighted average of the above means as weighted average mean is beta into weighted average mean to t minus 1 plus mean of t for t is equal to 1, all mini batches. And use the weighted average mean and similarity weighted average variance to perform batch norm on a test set. Then we use softmax regression. In the softmax, the output vector contains the probabilities, whereas the hardmax has one for the highest probability and 0 for others. Here, activation function is e to the power of z. So, let me tell you about my own experience with a neural network. All of us are handling differential equations. We can easily handle differential equations using classical techniques or analytical treatment. You can find an analytical solution or you can find a numerical solution. But can you really use artificial neural networks to solve nonlinear differential equations? You know that their relevance is there in physics, engineering, biology, economics, so on and so forth. We know about analytical solutions and they are having advantages as well as limitations. I don't want to talk much of math. In the numerical methods also we can have. And in the basic structure of a neural network, whenever I want to solve a differential equation, I am going to take nodes, which are nothing but neurons, the fundamental units of a neural network, similar to the biological neuron in the human brain. Each neuron receives input, processes it using a weighted sum, applies an activation function, and produces an output. Layers. You can have an input layer, the first layer where the data enters the network, hidden layer, intermediate layers between the input and the output that transforms input into something the output layer can use. Output layer, the final layer that produces the predicted result or classification. Example, simple feedforward neural network which we have seen already. Input layer, hidden layer, output layer. Okay. We can have a supervised learning, unsupervised learning. And in the applications to differential equations, supervised learning involves training a model using labeled data where the target output is known. In the unsupervised learning, training a model without labeled data where the target output is not at all known. In the application of differential equations, we require a data set where the solution to the differential equation is known at specific points. Example, either initial conditions or boundary conditions. The model is trained directly on a differential equation, trying to satisfy the equation without explicit solution points. Training data uses pairs of input-output data. Example is x1, y1, x2, y2, x1, yn, which are the known solutions of differential equations. But whereas in an unsupervised learning, uses only input data. Examples are xi and the differential equation itself to find solution that satisfy the equation. Target function. The model learns the approximate the true solution based on provided examples. Whereas the model learns a function that satisfies the differential equation across the entire domain without specific examples. Error metric. Error is calculated as the difference between the predicted solution and the known solution at specific points. Whereas error is calculated based on how well the model's output satisfies the differential equation. Idea is residuals. And what are the examples of use? Predicting solutions at specific points when solutions are partially known. Solving differential equation when the exact solution is unknown or only the equation is available in the unsupervised learning. Complexity, typically less complex as it relies on known solution containing, because you are having a target. It is unsupervised more complex as it requires the model to understand the differential equation and satisfy it without specific solution points. What about computation cost? Naturally, here less computation. Here, higher. Generalization may not generalize it well outside the provided data points. And idea is to generalize the solution across the entire domain. But that is also a difficult task. Because of my practical experience, I am saying that. This is a supervised, unsupervised learning. L of it is a mean square. Okay. Here, xj minus mu I. Okay. Requires labeled data, requires only input data. Produces the output based on input data, identifies underlying structure or grouping in the input data. Regression, classification, where the output is known. Clustering, dimensionality reduction, where the output is not known. Okay. What are activation functions and their purposes? Already we have been just now we discussed about various activation functions which can really pitch in whenever you want to have a specific problem of gradient descent. Okay, common activation functions sigmoid, ReLU, tan H. Sigmoid and tan H are often used in the hidden layers of smaller networks. ReLU is popular for deeper network due to its efficiency. Learning process, training. Learning networks, neural networks learn by adjusting weights of connections between neurons using a data set of known inputs and inputs. Just now we have seen how to handle a scenario where we need to have efficient updation of weights. Forward propagation, loss function. What is loss function? It is nothing but the error. Measures the difference between the predicted output and the actual output. It is a mean squared error for regression, cross entropy, or a classification. So it is a ReLU function, leaky ReLU, tan H, binary step function. It is a linear. It is a SeLU function, LU function, sigmoid or logistic, parametric ReLU. Like that, you can really define a function of your choice. So a small learning rate requires many updates before reaching the minimum points. The optimal learning rate swiftly reaches the minimum point. Too large of a learning rate causes drastic updates which lead to divergent behaviors. Okay. Backpropagation, rule of optimizers, common optimizers. Okay. What is backpropagation? The process of adjusting weights by calculating the gradient of the loss function with respect to each weight using the chain rule. You need optimizers. Optimizers adjust the weights of the neural network to minimize the loss function. In solving differential equations, the optimizer helps the network learn the correct function that satisfies the differential equation. What are the common optimizers? Stochastic gradient descent, simple and effective for large data sets, can be slow to converge. ADAM, adaptive moment estimation. It combines the benefits of ADA-grad and RMS prop. Maintains per parameter learning rates, improving convergence speed. widely used due to its efficiency and adaptability. So, optimizer in the saddle point, you can see red is a sigmoid, it is a momentum, NAG, ADA grade, ADA delta, RMS prop. Okay. Each color is going to have one. Optimization on a saddle point, you can see. What are the types of neural networks? Feed-forward neural networks, convolution neural network, recurrent neural network. Already we discussed it. It's a back propagation. Okay. Now let me tell you about a loss function. What is loss function? Loss is equal to 1 by n into dy hat by dy hat by dx by yi hat n fx whole square. It's a squared error where yi hat is the predicted solution, f of xi is the true function, and n is the number of data points. The residual loss ensures that the network's output satisfy the differential equation. You know, this is to be minimized. Boundary or initial conditions enforces the solution to meet boundary or initial conditions. For example, loss of boundary condition is y hat x naught minus y naught whole square, where x naught y naught are the initial conditions. Total loss combines the residual loss and boundary loss. So both should be minimized. Guides the DNN to approximate the ODE solution accurately. So that's the reason nowadays people are using deep neural networks. So what are the advantages? Universal function approximation. And networks have the ability to approximate any continuous function given sufficient data and appropriate architecture. This makes them powerful tools for solving differential equations, especially when the solutions are complex or difficult to express analytically. And what are the applications? These neural networks can model the behavior of the solution over the entire domain, providing a global approximation rather than just a local solution. Flexibility and adaptability. Neural networks are highly adaptable and can be trained on various types of data and different problem domains. They can handle different forms of differential equations, including linear, nonlinear, ordinary, partial differential equation. By adjusting the network's architecture and training process, neural networks can be tailored to solve specific types of differential equations with definitely better accuracy. Okay, though I have written high accuracy. So architecture of a deep neural network. DNNs are used to approximate the solution of ODE by representing the solution as a function that satisfies the differential equation. Architecture is same input layer, hidden layer, and output layer. Advantage, flexibility in handling nonlinear ODEs, ability to approximate solutions of high-dimensional spaces, and encoding boundary and initial conditions to the network. For an accurate solution, the neural network must satisfy the boundary and initial conditions of the ODE. Soft encoding includes the boundary and initial condition directly in the loss function to penalize the deviations. Hard encoding. Design the neural network in such a way that the boundary and initial conditions are inherently satisfied by the architecture. What are the implementation steps? Define the deep neural network architecture. Choose the number of layers and neurons, activation functions, and the other hyperparameters. Encode the problem constraints into loss function. Include terms in the loss function that represent the differential equation, residuals and boundary conditions or initial conditions. Train the network and validate results. Use optimization algorithms like gradient descent to minimize the loss function. Validate the results against known solutions or use cross-validation techniques. If I take a simple differential equation du by dt minus d square u by dx square equal to minus u cube with ux0 is equal to sin pi x u0 to e. If I use an unsupervised method, If I am using 1000 epochs batch size of 100, 700 loss function is 0.08, 800 epochs 0.09, 900 epochs loss is 0.07. You know, loss is decreasing, but epochs are increasing, sometimes loss is really increasing. Trend may not be universal. It is a neural network approximation, it is the exact solution. You can see the difference. They are not the same. Okay. And epochs 10,000 batch size 100, 9,700 epochs 0.0018, 9,800 0.0013, 9,900 you can see loss function 0.0014. Okay, I want your attention here. And if you take the another problem, d square u by dt square is equal to c square d square u by dx square with the given initial conditions. If I use a finite difference method, neural method, and if I am having 700 epochs 0.39, 800 0.40, increasing, it again 900 it is decreasing. And it is a finite difference solution, a neural network solution, it gives a better result. And here also 9700.325, 9800.37, it is increasing. And 0.36 doesn't mean that epochs are always give you the less loss function. Okay. And these are the hyperparameters on which we worked on a simple example for the demonstration purpose. Okay. And activation functions and optimization functions. And these are the epochs, these are the neuron, number of hidden layers and neurons, and these are the results we got. Okay. A graph of different neural network configurations and another problem. Okay. So, idea is for each nonlinearity, for each equation, we need to identify a particular activation function and a particular number of epochs and a particular number of neurons, a particular number of hidden layers. So it is not universal. You cannot really make a class of it. The experiments we have done reveals that. I confined my research towards differential equations in this presentation. In the crypto also we use lot many neural networks, but there are also some limitations are there. Because of the time constraint, I cannot really go into that. Okay. And what are the challenges? Computational cost, model interpretability, generalization to complex problems. Future directions, hybrid models combining traditional neural network models, advances in neural network architectures and training algorithms. And on top of it, we need to parallelize it. We need to use a HPC, high performance computation. Okay. Advantages and potentials of neural networks for solving differential equations. The choice of hyperparameters significantly influences the performance and accuracy of the neural network-based solvers for differential equations. Different problems may require different network architectures, highlighting the need for problem-specific customization. So these are some of the references. So the greatest success comes from having the freedom to fail. It is told by Mark Zuckerberg. So especially in the neural network research, so many failures we do encounter every day, but we need to overcome them. All of us are Indians. Sanskrit is the best language for artificial intelligence, NASA says. I'm not an expert in Sanskrit, but we can encourage youngsters to learn Sanskrit, and in the years to come, people may explore. And my acknowledgements, I would like to thank Dr. G. Sitaram Brahmam of TCS, who is my super senior as well as my collaborator and who taught me many things. And I would like to thank Mrs. G.V. Deepika. Now she is in SBH Tech team. She was my former colleague at Sierra Institute. And we wrote a paper together. We worked together for some time on neural networks. I would like to thank Mr. Sudeep Kaktor, a research student at the University of Michigan, and he started working with me when he was in BITS, and he did his dual degree, BTech, and as well as MSc in mathematics. And Mr. J. Harikarthikeya, who is from Upstocks, Bangalore, he also interacts with me. And all knowledge in final analysis is history. All sciences are in the abstract mathematics. All decisions we make have their rationale in statistics. All technologies for efficient use depend on computers. It was told by none other than Padma Vibhushana, Professor C.R. Rao. And I worked in C.R. Rao Institute for 10 years. I had the privilege of interacting with Professor Rao, and last year he awarded to the heaven in his 103rd year, 103 year. And such a legend, learned a lot from him, and not only from him, all the colleagues of C.R. Rao Institute. And Ajnana Timirandhasya Gnananjana Salakaya Chakshu Runmilitam Eva Tasmai Sri Gurave Namaha. Thanks, gratitude to my mentor, guide, philosopher, teacher, a true guru who held my hand in 1991 and hold it till his last birth last year. Last October, he passed away. He is my guru. He is my research supervisor. He was taking care of me even I became a professor also. It is not really great to become a professor, but you look at the affection, care he has been taking over me. He was constantly inquiring me about my progress, and he was instrumental in seeing that my learning curve always goes up. So because of his teaching and training, I could survive in crypto world for 10 years in C.R. Rao Institute. My pranams to my guru. Thank you all for your patient listening. I will be happy to take any questions, if any.
Thank you, sir, for your lecture on optimization of problems in machine learning. This is the time for question and answer session. We will unmute the mic. Those who are interested to ask the questions, you can ask. Sir will clarify your doubts. Please read. Your mic will be unmuted. Please ask the questions. Those who are interested to ask the questions, they can ask. Or you can post it in the Q&A box. You can post it in the Q&A box. You can post the questions in the Q&A box, or you can ask directly to the sir. Sir may clarify your doubts. Okay, sir. Thank you, sir.
Or you can send it to the organizers. In turn, they will send me. I will.
Sir, already it is Q&A box is already opened, sir, and all the mics are unmuted, so they can ask directly, sir.
Yeah.
Sir, very nice presentation, sir. Wonderful lecture, sir.
Thank you.
Sir. Thank you one and all for your good response and valuable support. Expecting the same cooperation for the remaining sessions also. Today's session concludes with a vote of thanks by our co-convener, Dr. T. Srinivas Rao Garu. Dr. T. Srinivas will present the vote of thanks.
Good evening to all. On behalf of the Department of Mathematics and the participants, I would like to express my heartfelt thanks to our today's resource person, Dr. P.V. Sundarananda Garu, who gave such a good information on optimization problems in machine learning. It is an established fact that machine learning includes expert systems, speech recognition, case-based reasoning, artificial neural networks, NLP, soft computing, and intelligent agents. Optimization is the process of minimizing the cost or the loss function through various algorithms that are being used in machine learning. This is achieved by finding the minima of loss function or cost function. The algorithm is optimizing. The major challenge is going from local optima to global optima. It is observed in all the aforementioned algorithms that mere computation power may not propel towards an efficient, accurate, and exact solution. This is a high demand for optimization in exploring the markets, threshold, and the benchmarks of trade-offs in machine learning. In this talk, Dr. P.V. Sundarananda Garu have discussed applications, limitations, challenges, and possible ways to handle optimization in constrained environment. Today's session has been enriched with Dr. P.V. Sundarananda Garu presentation on optimization problems in machine learning, which has inspired new ideas among the faculty members and helped to strengthen their research skills. Thank you, one and all. Feedback link is posted in all the WhatsApp groups. Please fill it and submit before 8 p.m. today. Thank you, one and all.
Sir, thank you very much, sir.
Thank you, Bashir.
Sir, thank you, sir. Thanks for
Thank you,
this.
Sundarananda Garu.
Thank you, sir.
Sir, namaste. Thank you. So I'm signing off.
Okay, sir.
Can I? Yeah.
Oh,
Yeah.
So please extend your cooperation, our future endeavors also, sir.
Yeah. It's always a pleasure.